Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 73. Now in the previous lecture, I had alluded to the fact that from this lecture onwards, we shall be looking into the chemistry of meteorites, asteroids, and some comets, etc. But I realized that before we get to that topic, I wanted to just quickly do a tutorial so that some important astronomical aspects, related to astrochemistry are discussed. So in this tutorial, we shall be looking into some key ideas which are actually astronomical, but they are very much relevant in the context of astrochemistry. Okay, so I'll begin with the very first question in this tutorial then. So the first question in this tutorial is going to be, what is the concept of line of sight in astronomy, and how is it useful in astrochemistry? So this is the question that we shall first begin with in this lecture. Now, in fact, if you talk to any astronomer, I mean, the person may be an amateur or a professional astronomer, they would always be talking about this concept called as the line of sight. The phrase itself is kind of self-referential in the sense that you can find out the meaning readily by just this phrase itself. What do you think the line of sight is going to be? It's going to be, some line along your sight, right? But what is that line? And what is that line that is so important in astronomy? Okay, and how is it relevant to astrochemistry is what we shall be looking now. So the line of sight can be roughly understood as, I'll just call this LOS. This is L. Okay, so your line of sight can be understood as the path along which light rays travel from a celestial body to an observer. Okay. Now, in many cases, it's not just our naked eyes. It is going to be some astronomical equipment, such as, for example, the observer can be a telescope also, or other astronomical equipment via which we sense light. Okay, so this is called as the line of sight. See, we use the word line, okay, but it is not one single line, because even though the star or some celestial object in outer space, even though that may be emitting as a point source, recall, probably a few lectures earlier, I told you that the further away some interstellar object is, further away a celestial object is, the more likely that it shall emit as a point source. But even though it's a point source, the light emitted is not just one line. So the line is in some ways a misnomer. Okay, so when I say a line, I'm talking about a path which has a finite width. So notice that this line, this note, this so-called line has a finite width, because you talk about not just several light rays reaching you, so there is going to be some kind of a width associated with this line. Okay, all right, so this is the line of sight. Why is it important in astronomy, and therefore also its relevance in astrochemistry? So recall the entire conversation in this lecture, for a major part of this lecture, not this lecture, this lecture series, okay, in this class, has been about detecting molecules. And how do we detect molecules? Well, we detect molecules by obtaining information from the light obtained from a star. The light which is emitted by a star, we receive it, and using spectroscopy, which involves a lot of fundamental physics and chemistry, right, we were able to understand and detect what molecules are present in outer space. Okay, so therefore the light which reaches us through a line of sight is extremely critical in detecting molecules. So LOS is important in enabling us to detect molecules. But it's not just some kind of a qualitative measure of detecting molecules. We can also use this concept of line of sight to ultimately determine the number densities that we were talking about all along. Okay, so the LOS, that is the line of sight, is also, this is point A, and B is also critical in determining the number densities of any particular species. Okay, so I'll just stop writing it here. So this is critical. The line of sight is of course important in enabling us to detect the molecules, but it is not just about detecting molecules. It's also going to be critical in determining the number densities themselves. Okay, and number density is a concept we have been repeatedly talking about in this course, right? So how do we do it? That is the next part of the of answering this question. Basically, I'm just going to be answering how is it that the concept of the concept of line of sight related to obtaining number densities. That is what we shall be answering, right? In other words, how does the idea of line of sight relate to getting number densities? You can call it, some sort of a sub question to 1. So this is 1A. The answer is, so along the line of sight, you measure some light, and because the line of sight has some finite width, right? Now, bound by both sides, of both the you can roughly call it both the peripheral parts of this line of sight. Okay, you know what I'm talking about, right? What I'm saying is, you have some area, right? Some area which is bound between the two lines which constitute the line of sight. Okay, so that emanates, okay, the line of sight emanates from, let's say, some star or a giant molecular cloud, in deep space. So let's say that the line of sight emanates, not the line of sight itself, but the light that reaches us to the line of sight. That the light which reaches us via the line of sight starts from a giant molecular cloud. or I would say a dense molecular cloud. In the ISM. Now, you kind of understand that this path of light, called as the line of sight, is bound by two lines. Now, it is emanating from a giant molecular cloud. So, the place where it starts from, it has some cross section, right? In other words, you can envision, right? Let's assume, for example, that these are the boundaries of the line of sight, and this is the observer, let's say, on Earth. So starting from the ISM, you have the line of sight via which the light is reaching the observer, and this is, let's say, some dense molecular cloud. Okay, the light carries information, from the molecules present along this particular layer, the top layer, let's say. Okay, so this is the dense molecular cloud, and it has a lot of molecules. So the light that emanates from the topmost layer of this dense molecular cloud, that reaches us along the line of sight. Okay, in other words, the area bound by the two lines constituting the boundaries of the line of sight, by two lines. Let's just call this line A and line B. And the topmost layer of the dense molecular cloud. Okay, and the topmost of a dense molecular cloud. I'll just call this DMC. Can be thought of as being a column. You understand, right? So you have like two lines over here and this specific layer, the top layer. So they constitute a column. So in other words, you have two lines, and then you have some kind of a monolayer, which represents the topmost layer part of the dense molecular cloud. Okay, so they constitute a column. And so, because this constitutes a column, now light is coming. I'll also add this here. Light through this column interacts with the molecules present in the top layer, the topmost layer, right, of the dense molecular cloud, and gives us a measure of number of molecules. This is very important. Okay, the number of molecules present in that single layer. So overall, this single layer, right, it is a two-dimensional surface. Please understand, we have completely ignored the thickness of the molecular cloud. Okay, right? We only have a single layer, and along this path, the light that we get, it contains information about the molecules present in this single layer. Okay. Now, because the single layer is a two-dimensional entity, we get directly from the line of sight what is called as, we get a measure of the number of molecules. So this measure is in terms of per unit area, or let's say per centimeter square. Now this number, okay, this per centimeter square number is what is called as column density. Now, so what is this column density? This column density reflects the number of molecules or species or ions present, along 1 centimeter cube area, right, of this topmost layer from a giant molecular cloud or a dense molecular cloud. So we get this information from the line of sight that we can actually measure the number of molecules present in the top layer. Are we clear? This is what is called as the column density. And notice that the column density comes as a direct result of measuring the intensity of the spectral signal obtained from outer space. Okay, right? Obtained from a dense molecular cloud in outer space. So you measure the intensity. Recall that. See, experimentally what you get, you only get the intensities, right? So from this intensity, you can actually compute the column density. Now, what are the factors that this column density depends on? I'll write them here. Factors upon which the column density depends. Okay, so there are several factors. For example, the dipole moment of the molecule whose column density is being measured. Recall, what is column density? It is the number of molecules. There are different types of molecules, right? So the magnitude of the dipole moment is directly related to the intensity, right? So therefore, larger the dipole moment, right, you can more easily measure the column density. So the column density therefore depends on the dipole moment of the molecule whose column density is being measured. This is one factor. The next thing is the degeneracy. Remember, we were studying in partition functions, assuming a local thermal equilibrium. There was the expression of, I think, the Boltzmann distribution, wherein we had the degeneracy factor also. So the degeneracy of this molecule whose column density is being measured, that is also important. The next thing is, it also depends on the magnitude of the partition function. Magnitude of the partition function. Now this tells you the importance of the why we spent so much time on deriving the Boltzmann distribution in this course, and why we had to study the importance of partition function, and it also makes an appearance in the Saha equation, right? This column density also depends on the magnitude of the partition function also. Please make a note. Okay. Next thing is of dipole moment, degeneracy, partition function. It also depends on the excitation temperature. Now, what is an excitation temperature? Well, for example, there are different types of excitation temperatures. You can talk about electronic excitation, vibrational excitation, and also rotational excitation. Hey, but when discussing about rotational excitation, we were discussing about the idea of a rotational temperature, right? Example, the rotational temperature, which is a measure of the energy that is required to transit between one rotational level to another rotational level, right? So depending on what property, that is like what kind of transition in the molecule that you measure the column density, this excitation temperature is also important. An example of an excitation temperature would be the rotational temperature that we discussed in the rotational spectroscopy module. Okay, so these are four factors. See, the excitation temperature is also related to the energy gap between any two levels. Okay. When I say level, I'm talking about the two different states, wherein the transition happens, via which the column density is measured. And it also depends on, the next factor is the frequency of transition. And EF followed by the frequency of the transition. So E equals h nu, right? So the frequency at which this transition happens, that is also relevant to calculate the number density. Okay. Then followed by the frequency of transition. The next point is, it also depends on the Einstein coefficients. Which is of course related to your transition moment integral, right? The transition moment integral, that is, I'm talking about the magnitude of this one. It is also related to the extinction coefficient. That is, recall we had an empirical equation I by I naught, right? That is typically referred to as extinction. So your Einstein coefficient, the transition moment integral, the extinction coefficient, etc. See, I did not introduce the phrase extinction coefficient formally in this course, but understand that it is related to the ratio of I by I naught. While we were discussing how empirically we can determine the diameter of a molecular cloud. Remember? Maybe, while we were discussing about Einstein coefficients and then the importance of spectroscopy, etc. All right. So these are the different factors. Of course, this is not an exhaustive list. There may be many more factors also, but these are normally the factors upon which the column density, which is a measure of number of molecules that are there in the topmost layer, right, of any molecular cloud, that can be measured. Please note this carefully. Okay, so this is what is called as a column density. Are we clear? Now, you may be wondering, why did I talk so much about all of these qualitative aspects? Okay, why did I not give a single formula? The reason is, there is no single unique formula to define the column density. Okay, depending on the approximations we make, there are different kinds of formulas. So all these formulae contain a variation of all of these parameters. Okay, I'll make it clear. Note, no single unique formula to get the column densities. Okay, it is only that there are so many formulae and so many approximations involved. For example, there are two prominent approximations called as the optically thick approximation and optically thin approximation, wherein the thickness of the layer, right? Different approximations are made related to the thickness of the topmost layer that we're talking about. So there is no single unique formula. That is why I did not give you any one formula which incorporates all these aspects. Just note that your column density depends on all these factors. And depending on the formula you use, you may be getting different numbers, but nonetheless, they all depend on these parameters. All right. So this is about column density. But now you could be wondering, all along in this course, until this lecture, I was talking predominantly in terms of the number density measured in terms of what? Per centimeter cube. But suddenly, hey, in this class, I'm talking about column density measured per centimeter square, right? So how do we then convert this column density into the number density we have been traditionally talking about? Well, that involves one more layer of approximation atop, using a formula which depends on all of these factors. And that involves making approximation about the thickness of the molecular cloud. Okay, right? See, we've got molecules, the number of molecules present in one layer. So that is going to be in terms of per centimeter square. See, I say one layer, but it has some thickness. Okay. Now, but beyond this layer, if I consider the entire cloud, so this is just this part. I'll say I'll put a small thing. Let's say this is the one layer, right? one layer with some thickness, but this is the entire rest of the cloud also. So once we get the column density, we then need to make assumptions about the morphology or the shape of the molecular cloud and make approximations about its thickness and then get the final number densities that we have been using all along in this lecture. Okay, from the column densities, the number densities this is so the column densities are per unit area, but the number densities are per unit volume. I've obtained by making various approximations about the thickness of the dense molecular cloud by making approximations about the thickness of the dense or not so dense molecular cloud. Once we include the depth factor also, from therein we can get the number densities. Okay, that's it. Once again, notice that there is no single unique formula for the number densities also. Note no single unique formula for number densities also. Please make note of this. Okay, so what did we see in today's tutorial so far? Well, I started off with the idea of line of sight, and I was babbling for quite some time, right, about how the line of sight has a finite width and how this leads to a column. And from the column, we can measure the column density. And from the column density, we can overall get the number densities themselves. And recall, of course, that there are going to be lots of approximations made. For example, approximations in the depth of the giant molecular cloud, and then approximations involving how exactly to input all these parameters in a formula, right? But despite all these approximations, we get some kind of an estimate of the number density, which is remarkable if you think about it. We are, I don't know, many parsecs and light years away from these sources, yet we can estimate, of course, approximately how many molecules are there. Isn't it remarkable, right? What all molecules are there and how many of each kind is there, right? So that is the advantage of using the fundamental ideas of physics and chemistry to get the number densities in the ISM. One last point for today's this tutorial will be that, please note this, the only experimental output, right? The only experimental output that we get are the line intensities. So using the only experimental output, that is the line intensities, we get so much of knowledge. We get so much of knowledge by applying a lot of physics and chemistry. Okay, please note this point. I will in fact write it down. Make note of this point very strongly, that from outer space, only output will be the intensities of the line. Right? When I say line, I'm talking about a spectral signal. Okay, and from therein, using a lot of physics and chemistry, we measure so many aspects, including number densities. We measure column density, number density, etc., etc. All right. So on that note, I end this tutorial and I'll see you all in the next lecture. Thanks a lot.